So hello everyone, welcome back. I don't know how many of you got an opportunity to look at the scripts which I shared it with you. I just made a few more changes. I just cleaned up a couple of messy things here. This is regarding the gradient descent. Okay, so this is the same script. I've used the same script, the gradient descent. Okay, and here only thing is I plotted the epoch. Okay, and so in the case of gradient descent, they will ask you this question. How do you determine the number of iterations? How many number of iterations that are required to minimize the cost? How do you determine that? So in that case, what we do is, look here, if you look at this script here, I just made few changes here. I have initialized two variables as a list. Okay, and here inside this, I just use append. You know very well how append works. So initially the list will be blank, and as and when for each iteration for for each iteration, when it computes the mean squared error, it will get the copied here. So which means the history will be captured here for each iteration. Okay, and append I, this is the iterations, how many iterations we store this for, right? Okay, so that with this we can plot the chart something like this. Okay, the history of the cost, we are storing it something like cost list, and iterations we are storing it in this one, so that we can refer which iteration, how much cost we got it. Okay, so and here I'm returning all the things, EMC, the slope, intercept and cost, and the history of the cost, and the history of the iteration. And finally, when I call this gradient descent, so this is my independent variables x, and y is my dependent variable. This is number of iterations. So here you can pass, I mentioned about the epochs also. So what you can do is you can pass an argument of the learning rate also here. Okay, the learning rate, and even m equal to c equal to 0 also you can specify it here, or you can leave it as it is here. Okay, and the learning rate we can specify it as an argument. And so with this three arguments, it returns four values. Look here, this is the 5 values, right? 5 values, I'm storing it in this variable. And when I see this one, it gives me for each iteration what is the it returns these values. Okay, and when I pass these values, and it gives me this is the one gives me these values. Okay, and when I plot this here in the x-axis epoch and y-axis cost, and epoch list and cost list. Cost list is holding the cost for each iteration, and here when I plot it, I can see that for this is 200th iteration, 400th iteration. So in this graph, we can see that the error reduces significantly here. Okay, but as iterations increase, there is not much, the errors occurs. So this is nothing but the cost is nothing but your error, right? It almost stabilizes from here onwards, right? So when you look at the error here, I just, okay, let me do one thing. I will just print this one. If you see here, let us check that one. So along with the iterations, we can see that the cost is nothing but the error. In the first iteration, this is the error. For this slope and intercept value, this is the error we are getting it. As the number of iterations increases, which means as the number of steps increases, the cost also decreases. As per this chart, somewhere here, right? So 100 or some, not even 100. This even just before this, it is stabilizing it. Iterations, let's say we say 100 approximately. So 111, or so, we'll take 100. 11.250, okay, and 11.187. Even if we take 200 approximately, it's all 1111, 0.623, 623, right? So it nearly stabilizes after a certain value, or we can say that it decreases negligibly, right? So we don't see significant decrease here. Just above, if you see here, 134, that's what, in iteration 65 itself, you see 117, and then 11, right? So 117, 113. After a point wherein, you can see what 111, right? So where it starts, the 111, 85 itself, good. So we can say number of iterations, 85 iterations are more than sufficient, okay? And with that itself, after 85 iteration, we don't see any significant increase, so decrease in the cost. We want to minimize the cost. We want to minimize the error by iteratively increasing or changing the values of beta naught and beta 1. For this beta naught and beta 1, sorry, the intercept and slope, we can see this cost. So even after the subsequent iteration, we don't see any significant decrease in the cost. Okay. The interview, they'll ask you, how do you determine your algorithm got converged, and how many number of iterations, how did you determine? So we have used the elbow method. This is called elbow method. What do you mean by elbow method? So here, exactly in this point, right? In this point onwards, it is stabilizing it. We don't see any increase. This is your error cost, right? As you increase the number of iterations, the error keeps falling. At one point in time, it has fallen down, and then it got stabilized. Afterwards, we don't see any improvement, no increase, no decrease. So exactly in this point, right? This is your elbow method. So using which, so in this case, we plot the cost list in the x-axis and in the epoch list in the x-axis, cost in the y-axis. And once we find the elbow, right? So the elbow is the place where we need to find out what is the value for this iteration. So this iteration is something like 85. To confirm that, I just printed all the things here. Right after 85, we don't see any improvement. That means fine. We can use 85 iterations or 100 iterations. We can use it. More the iterations, it will take longer time. It will come. It will unnecessarily consume CPU. So this is the way we can select the best possible value for the number of iterations using this graph. So this is called your elbow method. Fine. So the next one is, I have a few questions here for you all regarding a few review questions. What is the difference between cost function? This is regarding the gradient descent. What is the difference between cost function and gradient descent? Can you please, what is cost function? How many of you remember this? What is cost function? What is gradient descent? Cost function, nothing but error, right? Which we wanted to minimize. Cost is, you see, don't get confused with cost and cost function. It's all same. The cost function is we want to minimize, whereas gradient is a method for finding the minimum, right? So using the gradient descent, we are trying to minimize the cost. Gradient is an algorithm. Iteratively, it's an iterative optimization algorithm using which we are optimizing the cost. That is the difference between these two. And the next one is, can gradient descent be applied to non-convex functions? Yes, you might be, yeah, you are not familiar with this one. See, the one we have fitted the model, right? So the linear regression problem, right? So we have solved the regression problem. In the case of linear regression, we simply call this a convex function. Okay, don't break too much on this one. The convex function will be something like this U-shaped thing. You remember I explained you, so you are, somebody standing here, and to reach from point E to point B, they need direction and they need to know the step size, right? So this is nothing but the convex function. This is in the case of regression problem. In the case of classification problem, it will be like something like this, non-linear function. In the case of non-linear, it is going to be non-convex. Okay, this is not a convex, this is a non-convex. In the case of non-linear problem. So logistic regressions are non-linear. Okay, but here it is a linear. In the case of linear, it is called convex function. Yes, you can use the gradient descent for linear regression, even for the logistic regression or classification problem also we can use that. That is the answer for this. What is the difference between gradient descent method and the ordinary least squares method? What is the difference? Which one is better? I explained it, right? How many of you remember? The case of gradient descent, we need to iterate. We need to keep increasing. We need to find out the gradient, and then we need to keep updating the values for the theta naught until it converges, right? So that is what we do it. And in the case of ordinary least squares, there is no need for any hyperparameter. Whereas in the case of gradient descent, the alpha, the learning rate is the alpha was the hyperparameter, which means it is a tunable parameter. Anyhow, we are going to discuss about hyperparameter probably tomorrow or so. Okay, don't worry. So in this case of ordinary squares, no iteration is required. Okay, but if you work with huge number of data, then you need to go for gradient descent. It is worthwhile going for the gradient descent is if you work with huge volume of data. Whereas if you have smaller records, in that case you can better go for OLS. Okay, ordinary least squares method. That equation we used it, isn't it? So what is the learning rate in gradient descent algorithm? What is your understanding? What is the learning rate? So the learning rate is nothing but the alpha hyperparameter. Okay, and this is the value, right, using which we update the theta naught values, the intercept and slope after the derivatives have been found out in gradient descent. Once the derivatives for the theta naught and theta 1 has been obtained, so what we do is we update the learning rate. So we update the weights, right? So that is what learning rate. Okay, so but with the help of learning rate, by taking the product of learning rate into your dou by dou theta naught j of theta naught comma theta 1. Okay, this derivative time, right? You need to take the product of learning rate by this one. This is if you subtract this one from your current position, you will get the next position step size, right? Next position you will get to know step size. Okay, basically it is a learning rate. So using this learning rate, we can update the weights. We can simply say this one. Okay, and then the next one is name a type of error function used during gradient descent. This one you should be remembering it. Which function we use it? What is the formula that we used it for this error? So linear regression, how we use the same matrix here, isn't it? Which matrix that we use it here? We use it in which cost function? What is the equation for this one? The error. What is error? Can someone tell me? Type it in the chat window. What is error? Guys, if you I'll tell you one thing. The one mean squared error. mean squared error, right? We have taken the partial derivative on the mean squared error in order to get the gradient direction. Okay, we take that one. That is what very simple one. We simplify. See, even 2 years back, we don't have any good document to understand gradient descent. We were literally breaking. Okay, guys, this is the one. So we use formal notation. J of theta is equal to the same thing. 1/2 is equal to I equal to 1 to n. Instead of saying the predicted value, s theta of x minus the actual, this is your predicted value, this is your actual value, and square. That's it. Very simple thing to remember. See, oddly, I'll just mute it. Right. The error function is MSE, mean squared error. Okay, that is the thing. And this is the formal notation we use. What are the problems with vanilla gradient descent? This is nothing but the batch gradient descent. They use a different term. Vanilla is nothing but the batch gradient descent. We discussed about stochastic gradient descent. This is nothing but the batch gradient descent. Vanilla is nothing but batch gradient descent. You remember this. That's all. Okay, batch gradient descent and stochastic. In the case of batch gradient descent, for each iteration, it takes the entire data set to compute the value for theta naught and theta 1. Whereas in the case of stochastic gradient descent, for each iteration, it samples only one record. Whereas in the case of mini batch gradient descent, for each iteration, it takes only the subset of the data, some sample of your data, not the entire data, a subset of your data. Batch gradient descent, in the case of vanilla batch gradient, let's say you have let's say you have 100,000, 1 lakh records are there. It will take 100,000 records for each and every iteration. Whereas in the case of stochastic gradient descent, SGD, it takes only one record. That too, it randomly samples the value. First iteration 1, second iteration maybe 8th record, third iteration maybe 5th record. Okay, that's all. And since it takes only one record, the computation time is less, and arriving the cost, right, it will be much faster. But the next one is the mini batch gradient descent. Mini batch gradient descent. That is the one, instead of taking going to the two extremes, only one record, you cannot get the global minimum, right? And global minimum is this one. This is the point, global minimum or local minimum or global minimum. But instead of taking 100,000 records for each iteration, or instead of taking only one, we will take the subset of this data. Okay, in between, because if you take only one observations or only one example or record, right, so it will not be that accurate. Okay, so that's why many gradient, the mini gradient descent is popular. Okay, you can try all this approach and see which one is better. And I would suggest you guys to see, now I cleaned up all the mess. What you do is you take that assignment which I gave you, the multiple linear regression. Okay, you start fit this thing, use gradient descent for that. Okay, and then get back to me about your thing. It's all, you see, when our farm. All right, guys, so use the housing price, but in that case, you will have to use, you need to find out the gradient for, you will have multiple gradient, right? So how will you do this one there? So in that case, you need to use for each slope, you need to update this one. Okay, for each slope, you need to update this one. This one, you just think about it. I will let you know. First, do this, and then I will let you know in the meanwhile how you need to, because let's say you have, in this case, we have only one independent variable. Okay, if I have more than one independent, how to do that one? Okay, so that one I will, I will let you know later. At least now you do this, go through this, and start practice this one. Okay, fine. So next we will continue with the logistic regression part. Okay, before that, yes, what are the problems with this? Is the problem for each iteration, performance problem, it takes longer time to reach the global minimum. If you use this computation, it will take too much of CPU. That is one drawback with this one. So, okay, next